some process condition that gives you an indication of what, in the case of the pH, which is a very nonlinear process, the pH would give you an indication of more or less what the process gain would be. If you're really far from the transition point, then your process gain is going to be very low. Like you have to try to add or a lot of casting, or take out a lot of casting to change the pH. But when you add this titration point, then the process gain is very, very high. So you need a low controller gain to balance the very high process gain that you have in the middle there, where the transition is very high. So you need a low.
Like a software algorithm that give more gain on the two ends of the scale.
Exactly. You'll take a measurement of the pH in there, send it through a little function generator that will generate the controller gain, which differs based on what the pH is, and that goes into your PID controller. So the PID controller gets updated to match the pH every time. Right, so we're back on internally caused problems. We said there are quite a few valve problems. You've got to rule them out first. Otherwise, it could be a tuning problem. Controller tuning, various options there. One is you just stick it in with the default settings or the factory settings. It's not recommended, but I guess most of you have seen controllers that have just still got the default settings. You can use typical settings. On a flow loop, you might not be too far off. Use a gain, I don't know, gain of a half, an integral time of 30 seconds or so. And most flow loops would probably work okay with those settings. Not so on a temperature loop. When a temperature loop, some temperature loops need an integral time of 1 minute, some temperature loops need an integral time of 30 minutes. So typical, these two are not really good. I wouldn't consider them to be tuning methods. You can do trial and error tuning. Most people use trial and error tuning. But it's not necessarily the best way to tune controllers. Okay? Most people don't eat enough fiber, don't get enough exercise. It's not necessarily because most people do it that that's the right thing to do. All right, so it's convenient because you don't really need to know much about the process of the controller or anything. You just turn the gain up and down a little bit until you're happy with what you see. Better tuning methods would be to use tuning rules or tuning software. So you do a step test on the process, and I recommend doing more than one step test. Do one step test, there may have been a disturbance, the valve might have stick or something. So do a few step tests, then you calculate the process characteristics. If you use software, the software will do that for you. Then you've got to consider the control objective. Do we need to have this loop perform as fast as possible or kind of intermediate? Do we need this loop to be robust because the process characteristics change? We make different products. We need this loop to always be stable. Is overshoot really bad? Maybe a temperature loop. We can't tolerate any overshoot. So we've got to consider the control objective because you need to pick your tuning method based on your control objective. Surge tank tuning versus level controller tuning, two total different tuning approaches. Right, then once you know your process characteristics and you know what your end result should look like, then you can use an appropriate tuning rule or software to tune a controller. I prefer using software because it does a lot of things for you. But if you don't have software, you can use a spreadsheet. I've got a little spreadsheet that I use for tuning that I give away for free. If you like a copy of the spreadsheet, just put your name on the sign-up sheet at the back, or I've got a little sheet at the back, just check it. If you want a copy of the spreadsheet, I'll send you a copy of the spreadsheet. It requires you to put in a few details from the process, and then it comes up with a whole bunch of different tuning calculations depending on what your objective is. So Ziegler-Nichols, Golden Food, lambda tuning, tuning for long dead times. Here's an example. This was a separator level control loop. The loop was virtually unstable. They didn't really know why. So there's the set point, the set point's in green, the actual level is in blue, and you can see there's some oscillation going on. The operator raised the set point because we wanted to do some step tests, so we wanted to get into an intermediate level. So he raised the set point for us, and we still had some oscillations on the fuse. This is the controller output. You can clearly see on the controller output that there are oscillations. So what we did is we just basically just detuned the controller very quickly just to get things stable. So we detuned the controller, stabilized it. It wasn't the right tuning settings, but the loop was stable. Then we went to the manual control, did some step tests up and down, calculated the tuning settings. We put the new tuning settings in at this point, and the loop was quite stable, but the PV was still a bit noisy. And then we added some process variable filtering just to reduce some of the noise of the PV. So this loop had no other problems. It was only a tuning problem, so it was quite easy to address. There's also this combination of these two, cyclical interaction. It's kind of internally and externally caused. We often find that we have this pressure reducing valve, the high pressure, like gas is coming into the plant, really high pressure, and we want to control the flow, but the pressure is too high to control. So we've got this pressure reducing valve, and after that a flow control loop. And quite often, one of the two, you find the pressure loop is going to be a manual, because these two just hunt against each other. They just tend to oscillate. That's exactly this example. Well, not exactly this example. This is a minimum flow. But we have a pressure and flow loop, or two flow loops hunting against each other. If you have a strong interaction between two control loops, and they have similar dynamics, and you're using aggressive tuning, you're bound to get into this hunting situation. So you have a few options there. The one option would be to pick the most important of the two. We've got this pressure, we've got this flow. It may be more important to control the flow. So that's the important loop. We tune the flow for a nice fast response. And then we tune the pressure loop to have a response at least 3 times slower than the flow loop. And that way we break this dynamic interaction between the two. The pressure loop would basically be making changes so slow that the flow loop has time to catch up with whatever changes the pressure loop is making. It's quite common to implement multi-variable control if you have on a larger scale, if you have interactions between processes, to implement MPC also. That's as far as oscillations go. So I have a lot to say about oscillations because there are many causes for oscillations, and it's a very common problem. Moving on to the less common but also important problem, random deviations. We could have random deviations, could just be measurement noise, or it could be a disturbance. And the difference between the two is noise is really fast movements in the process variable, could be caused by turbulence, boiling, electrical noise, so fast movement in the process. And disturbances are more slow, and they sustain really. If you go off set point, it's off set point for a while and then comes back to set point. The noise is easy to deal with, reasonably easy to deal with. You can filter it. The controllers have a filter setting, many of them, or analog input card. Even the transmitter, we have a filter setting. Only use a filter when it's needed. You can have a loop work without a filter. Don't use a filter. It slows down the control loop. It affects your performance negatively. Apply minimum filtering. If you do need filtering, apply just as much as you need. Don't go and add a 3-minute filter to the flow loop. It's just as little as you need. And then retune the loop afterwards. When you add a filter to a loop, it changes the way that the loop dynamically behaves. So you've got to retune the controller. And then finally, disturbances. We've got this disturbance. It's affecting the process. Not much we can do about the disturbance. That's just part of the process design, but it sure is affecting our loop here much more than we'd like. Could be a valve problem, tuning problem, or it could just be that this disturbance is way too fast for the loop to handle. Valve problem typically would just be a deadband problem. So this valve has deadband, and the controller has to move through all of this deadband before it actually regains control over the process. So it looks like the loop is sluggish, but it's not really. This deadband is the controller. There may even be, if you take a butterfly valve, it has this kind of an S shape. So it's a little flat where it just opens, but then, well, the flow characteristic of a butterfly valve then goes up steep, and then above about 50% or so, there's really not much going on. That's like deadband up there. Right? If your controller finds itself in that part of it, it has no control over the process anymore. But when it has to slow down the flow, it's going to move all the way from 100% down to 50% before it actually starts having any effect on the flow. So that's like dead band. You should put a controller out the high limit on there to not have the controller go into that area. Could be a tuning problem. Now tuning you can always tune a loop slower, but you can't always tune a loop faster. I've got this simulation here of a temperature loop. The set point is the process variables in the top screen and the controller outputs in the bottom screen. So we can tune this loop slower, really as slow as we want, but that's not the objective. We're trying to reject disturbances, so we want to get this loop to respond fast. So as we make this loop respond faster and faster, we see more and more oscillations in it, and eventually the loop's just completely unstable. So there's like a speed limit for every process that we just can't overcome. You can't tune the loop faster than what the process allows, and that's mainly caused by the dead time in the process. So if that's the case, then we've got to use something else. Feed-forward control is very effective. You measure the disturbance and perform a control action directly on this disturbance that's happening. Ratio control is kind of a cousin of feed-forward control, so they can also do really well. Multivariable control, they have the ability to do feed-forwards. And depending on where the disturbance comes from, cascade control may also even out. This is just an example of a PV deviation without feed-forward, and then with a feed-forward, much less deviation. All right, so let me go through, give me a summary. Obviously, the whole talk has been about control loops that persistently perform poorly. Now, it might not be a tuning problem. If you walk away with just that, that's good. Okay, so there's lots of other problems. Don't always just address it with tuning. Do process tests to detect if you have any valve problems, stiction, hysteresis, oversized valves, positional problems. Because you've got to repair that valve. It's not a tuning problem, it's a valve problem. When you do tuning, it's way more effective to do the two-step tests, calculate the process characteristics, do the tuning based on that. You also got to know the limitations of tuning, the speed limit that I just talked about. Okay, so, and then the problem doesn't necessarily come from this loop, it may come from somewhere else. You always got to find the root cause of the problem when you go to fix it. If you need to add feed-forward cascade, I'm a great believer in keeping things as simple as possible. But sometimes you do need to add feed-forward, gain scheduling, or something else that can really increase your performance, control performance. So if you want to copy up the spreadsheet that I showed, or copy of the presentation, just leave your email address at the back. I'll be happy to send you it. Do you have any questions about anything I covered?
You mentioned the filtering on the PV side, on the process variable and sensor. Have you used a output limiter on the controller output to help with stick sheet, so that instead of moving the signal each time the controller sets it, you give up, say, 0.5% gap before it actually moves the signal to the valve?
I have, the short answer is no, I haven't done that. What I was kind of computing is what the effect would be of what you just talked about.
It's kind of an output filter, and it builds
like a dead band on the output.
Builds a dead band on the output, so that the controller calls a little bit bigger jump and makes the valve move more smoothly.
Okay. You're still going to have, when the controller output jumps, it's still going to be a jump bigger than the one that you like to have, possibly. Maybe a dead band on the PV side would be more effective, because then as long as you're within that range of the wheel band that stick-slip cycles, and you just tell the controller, it's fine. If you're anywhere close, just don't control it anymore. I think that might actually work a little bit.
This little trick is like so many of the others that only apply to something in a few cases. It's a nice tool.
There are always exceptions, yes.
What kind of software do you use, or would you recommend the tuning software?
you tried several different kinds?
I've worked with ProTuner and ExpertTune and Loop Optimizer of PIS. Actually, I worked with ProTuner and ExpertTune, and then decided, well, I'm going to write my own software, and that's this Loop Optimizer that's sold on PIS. Years ago, they bought it from my company. So I'm kind of biased. I think that's the best one. I know the others. I know what features they have that Loop Optimizer doesn't have, and vice versa. But my recommendation would be try at least a few of them and make sure that it's something that you understand, that you can work with, that meets your needs.
Since you import and export data, obviously.
Right. If that's a requirement to import export data, make sure your software can do that. If it's a requirement that you need this bell and whistle, you need to linearize pH loops, take a look for software that can do that. So yeah, I wouldn't recommend just one. I use Loop Optimizer and whatever else I need. James.
You spoke about characterization of your valve response when you have a positioner. Smart positioners these days have you can put in a characterized curve in there. I suspect that they do that by increasing the gain. When you increase, the curve has more distance between the points that you're putting in there for characterization. Do you have any experience with that, and what should we be careful of when we use those electronic characterizations?
All right. The characterization is a good idea. It's a better idea than having a nonlinear valve in there. I would recommend to do characterization in the DCS and not in the positioner, because if the positioner fails and 2:30 in the morning it gets taken off and put back on, the chances are that characteristic curve is not going to go back in there. So I do it in the DCS. Although the characteristic curve linearizes the valve, the valve still has to move more under some conditions and less under other conditions. And those places where the valve is very sensitive, you could have stiction problems and things happen there. So even though this valve may look linear, it may mechanically not be perfectly linear. It may have problems at the high end. But it's still better than having a non-linear loop in there for most of the cases. Does it answer your question, guys? Yes, sir.
In the same regard to James' question there, with the smart positioners, you start out with a new valve, new position, a baseline, and the two parameters. Is there any recommendations for general tuning parameters in the positioner itself? So I may not agree with the characterization or any characterization to be done in DCS, but how do you compensate for the original gain that the president when you commission it out with the digital control? I guess it's it's already there in the loop dynamics when you do your testing originally. As long as those parameters stay the same and the tuning stays the same, throughout changing the position of the reason around 2 years later in the valve dynamics to change, and then your controller, the digital positioner dynamics will change. Is there any recommendations for a general starting point for the dynamics in the digital positioner itself?
No, I don't really have just a general recommendation. The positioners, they tend to be very fast. They act like integrating processes. If you understand the difference between integrating and self-regulating processes, a valve with positioner device acts like an integrated process. So you would normally use very little, if any, of the integral inside a positioner. And they would normally have quite a high gain. But what exactly that is, I can't tell you. Some positioners I know have a multiplier in there. So if you put a gain of 2, the number that you put in is 2, but it's got a multiplier of 15 or something in there, so it actually uses 30, which I don't know why they do it that way. So the short answer is no, I don't have any general tuning recommendations. If you, using the auto tune would certainly be better than nothing. So the auto tune should stroke the valve, and should determine what the valve characteristics are from a positional point of view, and then come up with settings which are reasonably okay. But it may come up with a large dead band and just say, well, I'm not going to control this valve. If the controller output changes anything within 2.5%, I'm going to leave the valve where it is. And then you put that on a sensitive process where you really need the tight control, and it's not good enough for you. So take a look at, I would say use the auto tune, but then take a look at what the deadband settings and the interval settings and so on.
Hey, Bill, it's not a question, but kind of an answer to your question. When you turn on a smart tuner and you hit the start button, it'll start to feed that positioner up and down until it's like stop, start, stop. And then it's going to see how much pressure I need to allow, quick this thing, start moving it to be linear. So it sets all that up in this mirror when you start it. So there's the starting point right there.
Well, but that is a static. I guess maybe we're more lucky if you have a flow of actual process there. I guess the question is, when we do tune the valve, smart positioner, it is a static, no process flow. What is the effect of the process flow in conjunction? Basically, you have a cascade. You have a PID control in the valve, and you have your PID and the DCS going to be a master. What is the interaction? I guess maybe that's his question. If you tune the valve static fast, and then are they going to interact eventually when the process is started passing through?
I understand the question. I don't know if the process itself will change the dynamics of the position so much. It might, but I would think that if it's, so the process we talked about, the temperature could increase the friction in the valve, so the valve may slow down, and the pressure certainly would push back against the valve stem and the valve trim. But then I would ask, well, if that has such a big, if that makes such a big difference, are you sure that the actuator is sized properly? If it has such an effect, the actuator size should be as such that it can quite easily overcome the pressure of the process. Or use a valve that's not affected by the process pressure. Instead of using, my mind's kind of slowed down now, but instead of using a balance, use a balanced plug valve to help there. But so the dynamics, okay, so can it interact? Yes, the PID controller can interact with the position. If it's very slow, and you have a fast PID controller, the two will react. You're absolutely right. That a cascade control loop. With a cascade control loop, you should tune your outer loop to be at least 3 times slower than the inner loop. Luckily, positioners are quite fast, and they normally move in, well, depending on the valve size, but they move in 1 or 2 seconds. Your flow loops are normally tuned a little bit slower than that. So your flow loop may take 15 seconds or so to get to set point. So there shouldn't be the interaction. If you have the interaction, the positioners either slow down significantly or your flow loop is tuned too fast. All right, no other questions? Yes, no questions.
Yeah, I did have one more question. You talked about gain scheduling. What is the interval between which that you should test your loop to get the different tuning parameters? 10%, 20%, if you're going to do gain scheduling? Because you have to start from something.
Yeah, it depends really what the shape, how much curvature you have in the installed flow characteristic. If it's an equal percentage type curve, something that is pretty smooth, you can get by with 3 points. 3 points will one at the start, in the middle, and the end. It's already going to make it much better than just a linear curve in there. But it may be a little coarse, so I'd say 3 points, maybe 5 points. If you have a butterfly valve that you're trying to characterize, you might have to have a few points around the upper curvature, a few points around the bottom curvature. Today you might be looking at 7, maybe 9 points. But even then, like a butterfly valve, even if you use just 3 points, it's still going to be better than having no characterizer in there. So I'd say ballpark, I'd say 5 points. All right. Well, gentlemen, if you're interested, you can take a look at the book at the back there, Process Control for Practitioners. I hope you learned something. I hope you can go back with some ammunition of how to fix your control loops on site. And it's been a pleasure talking to you all and sharing the information with you.
A little appreciation gift for,
Well, thank you very much, James. Hey, this is great. Excellent, thank you. Thanks, I appreciate it.
Thank you, Jacques. Please, I know I have at least 4 people who have not signed in. We're not going to let you out of the room until we have your name on the list. Thank you. Y'all have a good day. We have a presentation in April on, let's see, what,